welcome everybody to our talk about data pipes, declarative control over data movement. I'm Lukas Vogel, and this is joint work with Daniel, Danica, Pinar, Tianzheng, and Alberto. So the status quo is that data movement often is a bottleneck in modern deep storage hierarchies. So you have a lot of different layers here. Each layer can either be local or remote. It could be persistent, or it could be volatile. And on each layer, you also have multiple different devices you could have. And all of these devices have various different properties. So they have different latency or throughput characteristics, different access granularities, and also optimized for different access patterns. And this, of course, is a good thing, because that means you can put the data where it fits best for your workload. But the problem is that this incurs a lot of data movement between those layers. So applications spend a lot of time moving data, and this can either happen explicitly. Example, you issue a p-read syscall and move data from your flash to your DRAM. It could also happen implicitly. For example, your CPU caches implicitly move data from your DRAM into the caches whenever you access that data. And this is a complex thing, right? So we have lots of different APIs that can move that kind of data. They use different protocols to do that. We even have some kind of eclectic instructions to manipulate the cache to move data there as well. And what all of these principles mostly have in common is that they involve the CPU quite a lot. So it can be really taxing on the CPU as well. Fortunately, there are some shortcuts, and we'd like to utilize those. Here you can see two, for example, like DDIO or IOAT, which can skip layers using DMA. So for example, DDIO can move data directly from the SSD into the L3 cache without the CPU involvement at all. So that's a great shortcut we'd like to utilize. And fortunately, those shortcuts now exist between quite a lot of different device pairs already. So we would like to use them whenever they occur. And we call those shortcuts in the rest of this presentation data movement principles, primitives. Unfortunately, those data movement primitives are often difficult to utilize, and I would like to give you two reasons why that is the case. So the first one is those primitives are often hard to control. So let's say, for example, we want to do some kind of external sort, have some kind of unsorted runs on SSD, and want to move them to our cores to then do the sorting. The normal way to do this would be to use p-read or whatever, move the data into DRAM, where it is then moved into the caches when it's accessed by the CPU core. However, Intel has an optimization here. They call this DDIO, like I said before, which directly moves the data from the SSD into the caches. And this is a great thing, because this greatly, as you can see on the left side, greatly increases throughput, even through slow SSDs, because it reduces the number of cache misses by quite a lot, as long as the chunks you load fit into L3 cache. So you would like to use that, because it reduces the traffic in the caches. However, it's a kind of like not easy to use, because as you see, you still just use p-read, and depending on how the system is configured, the data could take two paths through the system. And we actually don't really have a control over which path is taken, because the only way to disable or enable DDIO, depending on our circumstances, is to use some global undocumented MSR that Intel provides for some platforms and doesn't for others. And yeah, it's a bad thing. So it's nice in theory, but hard to control in practice. Second reason is primitives are often hard to target. Take another example. We have some data that's stored in DRAM, and we want to, like, for example, our runs are now sorted, and we want to move them to something where we have more space, like, for example, PMEM in this case. The easiest way to do this would just be memcopy, one single line of code, CPU moves the data over, great. However, there's a better way to do that. And this is a little known unit inside the CPU core, which is called IOAT. Was introduced by Intel in 2005 and since then forgotten by most people, I think. And the idea here is that you can use DMA to move the data without the CPU involvement, and freeing the CPU to do other stuff while you move the data. And if you could use this, this would be great, because this more or less triples the performance if you just take a single core, and also frees the core to do other stuff. The downside, however, is it's very hard to target. So this is the code. It's purposefully small, so you shouldn't be able to read it. That's the code you need to do this with SPDK. And it works, but it's hard to use. So you see on the right side, we have the same thing, but we now have two paths to go there. And the fast path that we would like to use is really hard to develop for. Yeah, another problem. So for those reasons, we think those primitives have to be rethought. The reason being they are hard to utilize and also hard to control. So they often use vendor-specific APIs that try to be transparent to the end user and often fail at that. You need varying APIs to use them. They often are unconventionally, or even if they are conventional, they're often not widely supported by a lot of operating systems. So the culprit, in our opinion, is this kind of implicit bottom-up approach that the hardware vendors take when they design new data movement primitives, because often those primitives are invented for a specific use case. In the case of DDIO, I think it was 100 gigabit Ethernet. They say like, okay, we need to move the data into the caches to be faster. And then they build a specific technology exactly for that. And that's great if that is your problem. But if you want to use it for something else, like in our case, to move data over PCI with SSDs, then it doesn't really work that well anymore, because then it breaks down. And Intel is proud of you not having to do anything, because they say it doesn't require industry enabling. It just does what it is supposed to do in the background. And this is great if that's what you want to do. But if you want to use it for something slightly different, you're out of luck. So we think for those reasons, we should propose an alternative. And this would be a declarative top-down data movement way. So the idea is that we build a unified abstraction that gives the control back to the developer on how to move data, and that is what we call data pipes. So the idea of the data pipes is, here you can see again the devices on the right side that we, for example, could support. On the left side, you see the CPU core, and then the paths that our data movement primitives can use throughout the system. The first idea of data pipes is that we introduce an abstraction, which we call resource locators. So the idea is now that every device on the left side is usually, the data on it can be referenced by some kind of C-style pointer or whatever. The idea is to build a type system on top of that. And this is what we call resource locator. So every data is behind some kind of resource locator. And this kind of makes the data location explicit. So no more implicit data movement is happening. You have to know where your data is. We then, on top of those locators, build pipes. And those pipes, as a source, always have one locator, and as a sink have another locator. The idea is that pipes move data from one position in the stack to some other position, and this is clearly defined. And this makes the data movement explicit and declarative. So you see, instead of bottom up, where data is just somewhere and accessing the data could move it implicit somewhere else, we now have a top-down approach which show our intention to the system. And then we have a framework below that then actually takes care of the data movement. In the happy path, like here, you see the color of the pipes correspond then to our primitives. We can just use a DMA optimized ways to move the data and use the hardware capabilities. But in cases where there is no pipe between two resources, we can also fall back to a software approach, of course. And now let's look at an example how this could look like in code. So take our earlier example of an external sort again. So we have some unsorted runs on SSD. We want to move them into the caches, sort them there, and then we'll put them back to DRAM where they later on can then be moved to a buffer. So how we do this is, first, we declare some locators where the data is in the beginning and where it's supposed to be in the end. So SSD and DRAM. Then for each core, we also say, okay, we want this cache of that core, of course. And then we just connect our locators with pipes. So one pipe up from SSD to the cache, one pipe down from the cache to DRAM. And up until now, everything is just declarative. So you just state this in the code. And now we actually run the stuff. So we first transfer data up, sort it, and then transfer it down again. Okay, so what's the advantage of this approach? So first of all, it's declarative. So instead of this bottom-up approach earlier, it's top-down. You tell the system where the data is, where it's supposed to be, and how you want it to be moved there. Secondly, it's composable. So because it's declarative, you can now like put in stops in between where you say, okay, now I want this data on a buffer in between before it's moved to the background storage. So the pipe doesn't care where the data is going to. It's just caring about where it's supposed to be spitting it out, and then you can connect it with another pipe to continue onwards. Thirdly, it's optimizable. So the idea is, for example, here, if you look at this, the threads that sort the data, they don't care where the pipe is moving the data to when it's coming out of the sorting thread. They just care that it's moved somewhere into background storage, and later on the merging thread is just concerned that the data is back into the cache again. So we can have two implementations for our background storage here. We can have one for PMEM, one for SSD. The pipe interface is the same, and then our runtime can even during runtime decide on where to move data, depending on how the system is configured. Then pipes are also configurable. So for example, our PMEM pipe that moves data from DRAM to PMEM, probably you should use the IOAT unit I talked earlier about. But you could also have a fallback for software if like the IoT unit currently doesn't have available capacity, or like we could also use non-temporal stores. This could be attached to the data pipe, so you can control that. Then it's also orthogonal to existing primitives. So the pipes don't care about how the data, like what primitives the system actually is capable of. So we can use what is already there. But on the other hand, if hardware vendors would come up with new data improvement primitives in the future, which we would very much like, we could just adapt to that as well and introduce new pipes to those primitives as well. So research agenda. Currently, data pipes is just a really small prototype that's implemented in a user space library that mostly uses SPDK. So that's hard to use and not really universal. So we like to fix that. One thing is what we would like to do is to have it inside the operating system. The first reason being, if you have operating system support, it could then be just a common baseline for multiple libraries in the user space that just can implement those for different programming languages. Secondly, this would also help us with the issue currently that our resource locators don't really work that way, because what happens now is if we like assume something is on DRAM and the operating system swaps that out, like we can't do anything about that because we're in user space. So if, however, the data pipes would be managed by the operating systems, we could reserve resources for our data pipes to make sure the data actually stays where it's supposed to stay. And we have an example how this could look like in the paper. So if you're interested in some kind of API, how a data pipe in the operating system could look like, please take a look at the paper. Secondly, we also think there's opportunities for cloud infrastructure vendors. The first one being, data pipes can make everything more predictable, right? Because you declare upfront where data is and where it's supposed to be. So that means you as a cloud vendor now know where your customers want to move the data. So that means you don't have to over provision as much because you can easier schedule data movements. And this means you don't have to deal with noisy neighbors as much and overall have less over provisioning. And secondly, data pipes could also again be some kind of common API, either exposed to the customer or as some kind of middle layer, which also would help you in the long term to migrate to new device generations. If like Intel changes something below the hood, you still have this common abstraction left. We also have a wish list to hardware vendors, which would be nice to have, but probably pretty far out, but still we like to ask. First one is we would like to have more access to the hardware. So for example, I showed you the examples of DDIO and IOAT. It's really hard to configure. So please expose those tuning knobs that are hidden behind MSR registers and whatever to us so we can more easily decide on how and where to move data. Please also give us more control over the caching layer. So for example, you see we use instructions like CL demote or CL flush or cache line write back. Like this is a lead key abstraction anyway. So if you have to manipulate the cache, at least you might have to want to have a little bit more control of that. Secondly, Intel's DMA unit still lacks quite a bit of features we would like. The biggest one is it lacks a lot of documentation. So it's really hard to find out anything about it at all. So please, Intel, give us more information about what you actually built into your system. Secondly, still has quite a low bandwidth, especially for smaller data transfer, which is important if you want to move stuff in and out of caches, and a limited number of channels as well. And lastly, there is a lot of device pairs where like this fast pass, like the pipes already exist, but there's still some places where it doesn't. And we would like for our DMA units to just have more reach. So for example, there is already proofs of concepts where can DMA data direct over PCI Express into registers. So why not have more pairs so we have nicer pipes to move data to more areas? So to conclude, we've observed the data movement is a bottleneck in data incentive systems. We think the existing data movement primitives are great, but really hard to use because they're very heterogeneous and hard to address. Therefore, we introduced data pipes as an abstraction that presents a uniform interface to the application to use. is top-down instead of bottom-up, declarative and explicit instead of implicit. Thank you for your attention.